Yeah, live started. YouTube live started.
Hello and good afternoon. The Public Outreach and Education Committee of the Astronomical Society of India welcomes you to the discussion series, Ask an Astronomer. I am Sarita Vig, and joining me are Professor Aniket Sule and Professor Harvinder Kaur from the ASI POEC. Also helping out with the organization are Samir Dhute and Dr. Crispin Karthik. Our eminent astronomer for today is Professor G.C. Anupama from the Indian Institute of Astrophysics, Bangalore, and our theme for discussion is supernovae. Professor Anupama will be giving a short presentation about supernovae, which will be followed by a discussion. I invite our participants and viewers to jot down their questions in the chat box. I would first like to introduce our guest astronomer and speaker. Professor Anupama completed her PhD from the Indian Institute of Astrophysics in 1991 on the topic Studies of Classical and Recurrent Novae. She is currently the president of the Astronomical Society of India and the dean at the Indian Institute of Astrophysics. She is the professor in charge of the Indian Astronomical Observatory and Center for Research and Education in Science and Technology, CREST. She is also heading the India TMT M1 segments group. Professor Anupama is the recipient of the Government of Karnataka's C.V. Raman Young Scientist Award for the year 2001. She is a fellow of the National Academy of Sciences and Indian Academy of Sciences. She has been the editor of the Bulletin of Astronomical Society of India between 2004 and 2010. She is the principal investigator of the Growth India project, which is a global network of telescopes for the study of transients. Her research interests include novae, supernovae, gamma ray bursts, electromagnetic follow-up of gravitational wave sources, activity in galaxies, and development of astronomical facilities. May I now request Professor Anupama to begin her presentation.
Yeah, I'll just share my screen. Okay. Good afternoon, everybody. And thanks for that introduction, Sarita. It's indeed an excellent initiative which has been started by the Public Outreach and Education Committee of the Astronomical Society of India. Having this Ask an Astronomer series where people can actually discuss with experts in the field. So without much ado, let me just start off on what I want to discuss about. This is on the objects called supernovae, one of my main science interests. So before we talk about supernovae, let me very briefly tell you about how stars are born. So stars are actually born in dense clouds of dust and gas, which are hydrogen rich in the form of molecules, and these are termed as molecular clouds. Shown here are some examples of such molecular clouds that we see in our own galaxy, where there is a very intense star formation or the birth of new stars happening. So what happens in these molecular clouds is that when there is a disturbance or some kind of a turbulence within these clouds, that can lead to accumulation of matter locally. So you can have small regions of knots forming in these massive molecular cloud regions. So with the accumulation of sufficient gas and dust, the more matter can be accumulated as the gravitational force of this region increases, and it tends to accumulate more matter. So with more and more matter getting accumulated, we can actually have that region collapsing under its own gravitational attraction. And when such a collapse of the cloud or that region of the cloud happens, the material at the center begins to heat up. So at this stage, we call that region as a protostar. Now, with the build of sufficient energy and pressure at the center of this region or the core of this region, we can actually have a condition wherein a nuclear fusion can start. Okay? And this will lead to fusing of the hydrogen in the core to form helium. When the nuclear fusion starts, this is when the object becomes a star. So this is the actual birth of a star. A star's evolution itself, that is from the birth to its end, the evolution, depends upon its initial mass. So the lesser the initial mass, the longer is the lifetime of the star. Now, a star spends most of its lifetime burning hydrogen to form helium. And during this phase, it lies on this locus here, this sequence, which is called as the main sequence. Okay? So this is when it is burning hydrogen to helium. That is a time when it is called as lying on the main sequence. And a star spends most of its time doing this. Okay? Now, depending upon the initial mass, a star can have sufficient material that after it has formed helium from having burnt the hydrogen in the core, it can fuse helium to form heavier elements such as carbon, nitrogen, and oxygen. So whenever these nuclear fusion reactions happen, there is production of energy. So it is this production of energy which in a certain sense prevents the star from contracting due to its own gravitational attraction in the core. So showing the same thing pictorially, if we take a star which has got a mass similar to that of our sun, which we term as the low mass stars. Now what happens in this case is initial phase, you have the gas and the dust, and then the formation of the star. Then the star is burning hydrogen to form helium. It's in the main sequence phase, and typically it lasts like about 10 billion years in this main sequence phase. And then at some stage, it evolves off the main sequence and it goes into a phase called the red giant. So as you can see, this is the region where it is in the giant phase. Okay. Now in this phase, what is happening is that the star is expanded out. Okay. So when it is expanded, it has cooled down. Now, because it has expanded, it has got a larger radius as compared to when it was on the main sequence. It is called a giant. And it is called red because it is cooler. And so it is emitting in the redder region of the electromagnetic spectrum. So that's why it is called a red giant. During the red giant phase, the star can lose the matter in the outermost regions. And that forms a nebulosity around the central core. In this phase, it is called as a planetary nebula. Now, eventually, this nebulosity can be lost from the system, leaving behind only the central core, which for a star like that of our sun is composed of carbon and oxygen. And such a star composed of carbon and oxygen, which is very dense, which is the dense core of the initial star which was formed, this is termed as a white dwarf. A white dwarf can, if it exceeds a certain critical mass, which is 1.4 times that of the sun, if the mass of the white dwarf exceeds beyond that due to accretion of matter by various means, the white dwarf will collapse and it can either become a neutron star or it can form a supernova. Now, if we take the life of a high mass star, again, this star is also forming from the gas and dust in molecular clouds, but the core which has condensed to form this star is massive. And what we call as a high mass star is typically the star which has a mass which is 10 times more than that of the sun, or even beyond that, 10 to say about 100 times more than that of the sun. Now, these stars spend less amount of time burning hydrogen to form helium, that is on the main sequence. They spend if you're taking a 15 solar mass star, it spends just about 10 million years as compared to the sun, which is going to spend about 10 billion years on the main sequence. A main sequence star forms a supergiant. Like the star, the sun will form a red giant. The main sequence star forms a supergiant. Okay. These supergiant stars are the ones where the core can collapse and give rise to a supernova. I'll talk a little more about how this happens in the coming slides. So this is basically the way a star evolves. Okay? It starts from gas and dust, and then it ends up very quietly as a white dwarf, or it can have an explosive death in the form of a supernova. So to repeat again, the end stage in the life of a star is the explosion of the most massive stars, or the explosion of a white dwarf which is crossing the Chandrasekhar limit. Observationally, how does it manifest when the supernova explosion happens? Okay. Observationally, we see a very bright star at a location where there was no star or there was an extremely faint star. So you can imagine that there is a whole lot of stars and suddenly there's a new star, okay? And it's extremely bright. So hence the name supernova. Nova means a new star and super is for the brightness. It's extremely bright. Yeah. Sorry. So how do we classify these supernovae? Okay. There are a lot of supernovae happening in the universe. Are they all the same? No, they are not. So how do we classify them? The main classification is based on the spectrum that we get from these objects. And in the spectrum, the lines which are present due to the different elements, based on this, we classify the supernovae. Okay. The supernovae which show hydrogen predominantly in the spectrum in the very early phase, these are termed as the type 2 supernovae. And all the supernovae that do not show hydrogen are termed as the type 1 supernovae. Amongst these type 1 supernovae, some of them are arising from a white dwarf progenitor, and the others are arising from the collapse of a massive star. So basically, the type 1 supernovae are the result of an explosive thermal nuclear burning in the white dwarf. And this explosive thermonuclear burning in the white dwarf happens when the white dwarf collapses, the core collapses onto itself. Okay? And the outcome of this explosive thermonuclear burning, it causes the fusion of the carbon and oxygen atoms which are present. And it leads to the ejection of material which is dominated by the ion group elements, including nickel. Okay? The outermost regions of such a white dwarf are rich in the silicon element. So the progenitors of a type 1a supernova are of two types. I said this happens when the white dwarf increases its mass. So it has to increase its mass in some manner, and this is by accretion. The accretion can happen by it being in a binary system where the other component is a main sequence or a giant star, or it can happen by accretion in a binary system where both the objects are white dwarfs. So if we consider a binary system where both the objects are white dwarfs, we call these systems as the double degenerate progenitors. So you have these two white dwarfs in a binary system. They are orbiting around each other. And during this process of orbiting around each other, they tend to lose their angular momentum. When they lose their angular momentum, they come inwards. So depending on how close they come and the amount of angular momentum lost, they can spiral inwards. And at some point of time, they coalesce they merge, and when such a merger happens, two things can happen. Either it can form a neutron star and have a sort of a quiet death, or they can merge and have an explosive merger. And when they have the explosive merger, that is when it leads to a type 1a supernova. Now, if we take the case of a single degenerate progenitor, that is where you have the white dwarf and where the other object is a mass-losing ordinary star, a main sequence or a red giant star. So in this case, what can happen is the white dwarf is generally more massive as compared to the companion. So the white dwarf attracts material from the companion onto itself. So in principle, over millions of years, by this accretion of matter, the white dwarf can increase its mass. And when that happens, it explodes and gives rise to a type 1a supernova. When such an explosion happens, the companion itself is ejected away from the system. So here is a short movie showing this. You have the white dwarf, which is accreting material from the companion object. And as it is accreting material, it can increase its mass, and it reaches where it has increased the mass so much that it explodes. It explodes, the companion is kicked away from its system, and all that you're left behind is some kind of a nebulosity. So that is how we have the type 1a supernova arising out of a low mass star. On the other hand, what happens in the case of a massive star? Okay. Massive stars lead to the core collapse supernovae. Okay. So as I already mentioned, the stars with an initial mass which is greater than 8 solar masses are the progenitors of core collapse supernovae. In these stars have enough material in the core for it to synthesize elements all the way from hydrogen to forming iron in the core. So in these massive stars, you have an iron core as shown here, and you have layers of other elements where some amount of nuclear fusion is still happening in all these outer layers, but at the core you have it dominated by iron which has formed. So what happens when iron has formed in the core? You cannot have further fusion beyond iron, and this is primarily because the iron atom is a relatively far more stable atom as compared to the other atoms. So it has an atomic structure which is more stable, and hence this requires tremendous amount of energy if you need to fuse iron. So it's like basically there's no further fusion beyond iron in a normal manner. Okay. But you have mass continuing to flow into the core from the outer layers by the silicon burning which is happening in the outer layers, leading to continued formation of iron which is coming into the core. So the density of the core is increasing, and you have the protons and electrons which are there, they combine, they form neutrons. And during this process, neutrinos are formed which release energy from the core. So when this happens, there is this sudden loss of energy, and it's like that the core can no longer withstand itself under its own weight. So it collapses, or there is an implosion. Okay. So when this implosion happens or the collapse happens, the regions around the core plunge into it. Okay. But then the core is very dense, so it is almost rigid and incompressible. And this leads to a rebound, okay, a rebound shock kind of. And this shock wave, which is created as a result of this implosion and the rebound, this shockwave transfers, it results in a tremendous amount of energy, which is transferred to the outer layers that we had seen around the core. And the outer layers get this energy, which is then, it pushes the outer regions out with extremely high velocities. So the outer regions get a tremendous amount of kinetic energy, which pushes the layers out. So when this happens, there's this energy which is released into the outer layers. The outer layers are expanding. So this causes an immense increase in the brightness of the object. And that is how you see these extremely bright objects as a supernovae. And when this happens, the brightness of a supernova is so large that, in fact, it can dominate the entire galaxy. Its luminosity is dominating beyond the luminosity of its host galaxy for some amount of time. So subsequently, what happens to the core itself? After the core has collapsed, the supernova has formed, what happens to the core? Depending upon the mass, which is there, the ion core mass, you can either form a neutron star. That is, if the core mass is about 6 solar mass or less than 6 solar masses, then the collapse will lead to the formation of a neutron star. Now, if the neutron stars are rotating, then they are the ones which are called as the pulsars. So you can either have a neutron star or a pulsar surrounded by the nebulosity. If the mass of the core is greater than 6 solar masses, when it collapses, it can form a black hole, and around which you can have this nebulosity. So a core collapse supernovae leaves behind a neutron star or a black hole and a nebulosity around it, whereas a type 1a supernova doesn't leave behind any stellar remnant except a nebulous remnant. And this nebular remnant, in fact, does interact with the interstellar medium which is around it. And because the remnant is moving with much higher velocities than the interstellar medium, and it has a higher density, when it interacts with the interstellar medium, it can give rise to shocks in localized regions, and this shock will excite the atoms in the nebula which is there, and you get all these kind of very beautiful emission due to the various elements which are present. By and large, supernova remnants are very bright in the X-ray and in the radio, and this is primarily dominated by the shock interaction which is happening between the supernova nebulosity, the supernova material and the interstellar medium. So why are we interested in studying supernovae? Obviously, supernovae tell us a lot about the star that evolved into the supernova. It gives you an insight into the lifetime of a supernova. And because the material is released out when the supernova explosion happens, you know the various elements that are synthesized in the evolution in the lifetime of a star. So in fact, supernovae are the source of most of the elements in the universe, except hydrogen, helium, and lithium. And therefore, they're excellent laboratories to study the nucleosynthesis in stars. And when this happens, when the supernova explosion happens and the material is released, it goes and intermingles with the rest of the material in the galaxy. It'll enrich the chemical elements present in the galaxy. So it leads to a chemical enrichment of the galaxy. And this interaction that it has with the interstellar material, which is primarily again composed of molecular gas and clouds, can give rise to turbulence in these molecular clouds. And the turbulence, as I said in the very beginning, will give rise to concentration of matter, and this concentration of matter can give rise to new stars being formed. So supernova explosions will influence the dynamics of the interstellar gas and also regulate star formation in a galaxy. And this star forms, and again, depending upon its mass, it can become a supernova. So this kind of a star-gas-star life cycle continues. And supernovae influence this life cycle very heavily. Also, another reason why they're very interesting is because they're very bright and they occur in all galaxies. So they occur at all cosmological distances, even in the most distant galaxies. And because of the luminosity, we can observe them to distant sources, galaxies which are fairly far away. So hence they are one of the best cosmological probes that we have. And indeed, it is a study of the type 1a supernovae which led to the concept and the discovery of the dark energy, for which the groups which studied these objects and found that the acceleration and the deceleration due to the dark energy got the Nobel Prize in the year 2011. So another reason why supernovae are interesting is because, as I said earlier, they form these neutron stars and black holes. And when neutron stars and black holes merge, they give rise to gravitational waves and the gamma ray burst events, and they give rise to these, extremely exotic phenomena. And when the neutron stars merge, they tend to make some of the heaviest elements in the universe, and some of the heaviest elements that we see, which cannot even be synthesized during a supernova explosion, are actually synthesized during these neutron star mergers. So here is the periodic table, which I showed earlier, but I'm showing this once again, where clearly the source of the elements in the periodic table, as it is coming from the cosmic source of the elements, are shown here. So as it has been said time and again, we are all born of stellar material. So I will stop my presentation with it's a very brief movie which has been made by NASA, and this is just a recap on how supernovae are formed, the 4 different ways to form a supernova. So the first is a type 1a supernova, where you have a white dwarf and another star orbiting. So the white dwarf can blow up by accreting matter and form a type 1a supernova. The other way of the white dwarf merging, they coalesce, they get too close, they collide, and then they form a supernova. Then you have this massive star where the core gets too heavy, it collapses and forms the supernova. So yet another type of supernova is where the core collapses, but prior to the core collapsing, it has ejected enough material that when the core collapses, this material interacts with the pre-supernova material and becomes supernova. So these are the 4 different ways of forming a supernova. Thank you. I think we can take some questions now. We can have a discussion.
Yes, thank you, Anupama, for that very enlightening discussion. Now I invite Aniket Sule and Harvinder to join in the discussion. Aniket, you can start.
Yeah, thank you, Anupama. It was a very nice presentation. So when we were growing up, we always used to think that supernova means some star which is going to explode. But as you showed in the presentation, that the type 1 supernovae are mostly about the white dwarf stars, which have already gone through one stage of what we can say stellar death. So they go to the second stage, and that is one source. So what fraction of the supernovae which we see are type 1 and what fraction are type 2?
That's a good question. Okay, so the number of the type 1a supernovae are well, I mean, observationally, the type 1a supernovae are brighter. So you tend to see more number of them, as they're brighter than the core collapse supernovae. So you tend to see more number of them. And although the number of low mass stars are generally more than the high mass stars, it's not that all white dwarfs can lead to a type 1a supernova. By and large, the slightly more massive white dwarfs, that is, the white dwarfs which are probably already closer to the Chandrasekhar limit, specifically these when they are in the single degenerate system, these lead to 1A supernovae. And of course, of late, we have been seeing cases of two low mass white dwarfs, merging and giving rise to supernovae of type 1A. But yeah, observationally, we see more number of type 1A supernovae.
That is observationally by telescope. So, on the other hand, the historical supernovae which we have seen within our Milky Way, they are mostly type 2 supernovae, probably.
Yeah, I mean, it appears to be that, yes. And people are, analyzing the supernova remnants, the composition of the supernova remnants, and even after hundreds of years, this is actually giving us information about what is the nature of the progenitor by analyzing the supernova remnants which are present in our own galaxy.
So, most common question which many people want to want answer for is: are we likely to see supernova in our lifetime? Naked eye supernova.
You mean a naked eye supernova?
Yeah.
Ah, okay. Well, I already saw it in my lifetime. Supernova 1987A, which happened in the Large Magellanic Cloud, was a naked eye supernova. So, yes, people have seen it.
Yeah, for most people, most of the India, that was a bit too low to
yes, that's
to be spotted. But yes, some people definitely saw it.
Yeah.
There was a lot of news about Betelgeuse in the recent past. Some statements which were confused, were very confusing. I think the scientists made some statement in some popular talk, and then some media channels blew it out of proportion, and people started thinking that Betelgeuse will become supernova any day.
Oh,
So,
yes.
what is the status with Betelgeuse?
Okay, see, Betelgeuse is a high mass star. Okay, and it's a supergiant. So it is likely to blow off as a supernova, but not anytime soon. And in fact, why people thought it is probably, why there was this confusion is because it suddenly dipped in its magnitude. Okay, the brightness was, I think it came down to almost 50%, I mean 80 to 50% of its normal brightness. In fact, even now it is slightly fainter than what it usually used to be. So people thought that it could explode soon enough because, as I showed in that movie, there was the last type of supernova which was there. Okay. Now these objects are really massive objects which are known. There are these objects which are called, for example, the luminous blue variables, and certain type of supernovae occur in these massive objects where the mass loss has occurred just a few years before the supernova explosion takes place. Right. So probably a bit of the confusion was that people assume that Betelgeuse is going through this pre-supernova mass loss phase, and it is because of this mass loss that it has dimmed, because the material is obscuring the central star, and it has dimmed, and post this heavy mass loss phase, in a few years, it can become a supernova. So that is the reason why people thought that, okay, now Betelgeuse is going to become a supernova.
So
It
let us
will
take.
most likely become a supernova, but probably not very soon.
Yes, nobody can exactly predict
Okay.
when it will happen.
Exactly, yes.
So we'll take one question
Okay.
from audience.
Yeah.
Yeah. So
So
Sarita, you
there
want
is
to?
this,
Huh.
yeah, I was wanted to tell there is this question by Ashirwad who wants to know why are the type 1A supernova the standard candles like Cepheid variables, and are there any examples of distance measurement with both candles, that is both Cepheid variables and type 1A?
Yeah, that's a good question. Why are the type 1A treated as standardizable candles is because, by and large, a type 1A supernova occurs when the mass of the white dwarf crosses the Chandrasekhar limit, which is 1.4 solar masses. So, a majority of the type 1A supernovae started off with a white dwarf having 1.4 solar mass. Okay. So, they all have 1A supernovae, that they all have to have the same amount of energy released during the outburst. So that is why they are the best cosmological candles that you can have. And yes, there have been type 1A supernovae which have occurred in nearby galaxies where the distances have been measured using Cepheid variables. There have been differences in the distance measurements by Cepheid variables and by the type 1A supernovae. There are several observational biases that people are looking into in greater detail. These differences are narrowing down with better and better techniques, and hopefully we'll arrive at a stage where the distance obtained from the Cepheid variable and from the supernova type 1A agree within measurement errors.
Thanks, madam. Very well explained. Thank you.
Thank you.
Okay, so there's another question by Sri Lakshmi who asks, how significant is multi-messenger observations towards supernovae? Are there dedicated neutrino observations being carried out? What are the very first observational signatures of supernovae? As in GRBs, we have prompt emission followed by afterglows. Are there similar phases?
Okay. Multi-messenger observations are definitely significant because, as I mentioned, when you have a core collapse supernova, you have the neutrinos taking away the energy. And in fact, much of the energy during the collapse phase is taken away by the neutrinos. So the detection of neutrinos is something that is what the dedicated neutrino observations can give us. And supernova 1987A had a few of the neutrino events from that event detected, and that really helped us in saying that yes, nucleosynthesis is happening, and when the supernova collapse happens, there are neutrinos being released. So this kind of gave an observational verification of the theoretical models that one had. Okay, so so neutrino detection would definitely be the first observational signature of a supernova, if we have sensitive enough neutrino detectors for that. Definitely yes, but by and large, the first observations that we see from a supernova are in the optical region, in probably just very rarely, in very few cases, it has been seen in the X-rays, and that is for the really massive core collapse. And we do see these days, because you have these dedicated surveys, and you can observe a supernova very early on, within, for instance, the first 24 hours after the collapses happened, we see the signatures of the shock breakout itself. So these are some of the first signatures that we see from a supernova explosion.
Arvind, there were some questions from YouTube last time, right? Maybe you want to ask them? There were some viewers who had some questions.
Yes, I can. One question was, can you please talk a little about white holes? That was last time when before we broke. And there are two more. Before that, probably who are watching, we can take their questions first. One is from Biswajit Banerjee, who's written, since Professor Anupama works in the field of EM follow-up of GW, it would be great if she can say a few things about the EM follow-up of the GW waves. Thanks. Gravitational waves. This is the question, yeah.
Okay, the EM follow-up of gravitational waves can be a separate discussion sessions by itself. But what I can just tell you is that these gravitational wave events can give rise to electromagnetic radiation. You can expect to see, and it has been seen in the single electromagnetic event that was detected by the neutron star merger. So we could see it in gamma rays, in X-rays, in optical, infrared, and even now you can actually see it in the radio. So yes, it does give rise to all these events. And the EM, what gives rise to the electromagnetic radiation is something similar to what you see in the GRBs. Okay, it's a very similar physical phenomenon. I would, Sarita, I strongly urge you to have a separate discussion session on this.
Yes, yes. The next question, Harvinder, there was another question, right?
There was a request. Do you have
Okay.
an animation or visualization lab to simulate such phenomenon?
Animation.
This is from Amrut Desraj. Do you have an animation or visualization lab to simulate such phenomenon?
I think more about simulations. He wants to know
Simulation.
about the simulations. Yeah.
Whether we
So
can do it here or not. Yeah.
No, I mean, I per se don't have it, but there are groups which do these simulations, and you just go on Google, you can see a lot of these simulations. But I don't work in that field. I mean, I do mostly observation.
Yeah, I think the question probably is more related to are there opportunities within India to do these kind of dedicated simulations?
I see. Okay. I'm not aware of any group within the country which does the explosion simulations. If you're looking at the research aspect of it.
But obviously, if they're good computer simulators, they have other areas of astrophysics where their expertise will be useful.
Yes, definitely. Yeah, yeah.
But I was just curious also about this, that when exactly does this explosion occur? Because I think people are still working on that. So there was a curiosity, like we have these various phases. Let's say we are talking about a core collapse. Then at what stage what prompts this explosion?
Actually, till date, none of the theoretical models or the simulations have been able to reproduce the collapse. Most of the work, what they do is that it's like the collapse has happened and what happens after that. Whereas
Okay.
the type 1As, there is a little more better understanding on the thermonuclear explosion, the kind of, whether it is by detonation or deflagration method. So there is a little more understanding of that. But how exactly the core collapses is something which is, they've not yet been able to replicate it and show and do something which replicates the observations.
There was also another question, I think, which many people have, is that how do astronomers know there's a supernova explosion going to happen in some part of the sky? Because you have to be in the right place and the right time to catch it.
True. There could be a lot of supernovae that we have not been able to detect because,
Yes.
we were not looking in that direction. So, for example, earlier, say 20 years back or 30 years back, there were very few supernovae being detected. Okay? And by and large, most of it was by amateur astronomers who would keep looking at the sky. They had this passion and suddenly they would see a supernova. There were very few automated searches those days. But now there are dedicated searches dedicated for observing a search for transients. And again, it depends upon the cadence of each search. By cadence, I mean, how soon the survey comes back to observe the same object. Okay. So each of these surveys have their own target that they keep looking at, areas of the sky they cover, and they so that's how nowadays you find several supernovae. Typically, something like 6 to 7,000 supernovae are found, and when the LSST comes on, online, that is the Vera Rubin Observatory comes online in a year or a year and a half from now. It is expected that we would have something like about 200,000 supernovae being detected in a year by LSST.
So broadly, how do these automated things work? I mean, how does it know that, I mean, this is where it happened, and how quickly are you able to go and catch it up? Because I think the duration, it doesn't last long, isn't it?
Yeah. So how they work is that these so they're doing the survey of the sky. Okay, let us say they're looking at certain regions of the sky, and they keep revisiting those regions. Now, some surveys have a cadence of 1 day. That is, what it means is that tonight they have observed a certain region. So let's say they have observed a certain galaxy, and they come back tomorrow again to observe that galaxy. And they do a difference imaging. So today we have observed it. Tomorrow I come back and again observe that galaxy. I subtract one image from the other. Now, when I do this subtraction, then all the objects which have the same magnitude, where the magnitude has not changed, will all get subtracted out. And only those objects which have varied in their magnitude, that will remain. And some objects which were not there suddenly pop up. So these objects which suddenly pop up are the ones which can be supernovae or novae or any of these suddenly erupting variables. So there is an alert system, and immediately the information is sent out that in such and such a galaxy, these are the coordinates, a new object has been seen, and then you have to have follow-up observations. Some surveys, like for example, the Zwicky transient survey, they have their own sequence of follow-up, and they can, if they think that an object is extremely interesting, they do an immediate follow-up photometric and spectroscopic so that they can classify the object, or the information about a new object is sent out, and people who are interested, they immediately take a spectra and then it is classified. So this is how you try to you observe and find out these new objects. So the basic technique is the differencing technique.
Okay. Thank you. Aniket and
Anupama,
Harbinder.
yeah, Anupama, there is one more question in YouTube stream. Is CERN related to this topic since they have tried replicating certain events?
I'm not aware of that. I don't think so. I'm really not aware of that.
Thanks, Anupama. You mentioned LSST while answering one of the earlier questions. So, what is LSST? Can you tell something more about that?
So LSST is a 8-meter telescope which will come up in the southern hemisphere in Chile, and it's a wide field. It's got a wide field of view, which means it can cover large areas of the sky at any given in one exposure. And it is dedicated for, it's a survey telescope. So it'll keep revisiting the same part of the sky with a certain cadence, and hence it can discover a lot of variable sources. So it's basically a 8-meter telescope which is going to do the survey, and
So,
it will be the
who is
largest.
building this telescope?
Sorry.
Who is building this telescope?
Yeah, this is a US led project.
Okay. This is slightly off topic, but since we are on this topic, many people always think that why so many of these telescopes are in Chile?
Why?
Why so many of these big telescopes are located in Chile?
Oh, okay. Yeah. See, we try to locate telescopes in at those sites where you have the least light pollution, you are least affected by a lot of pollution created by humans. You are least affected by the atmosphere in a certain sense. So all this leaves you behind with very few locations on Earth, which fits in and gives rise to a place where you can do very good astronomy. So Chile has some of the best sites. It has sites which have the largest number of clear nights in a given year. It has mountains, so it has high altitude sites. So high altitude sites mean that you have lower ambient temperature, which means you can observe in the infrared region, and also high altitude sites which are in Chile, the population is fairly sparse. So these are located in sparsely populated regions. So human pollution is less, and so the night sky is really dark. It is not affected by the city lights and other things. Another major advantage that several sites in practically almost all the astronomical sites in Chile have is the atmospheric turbulence there is very low. And this is because most of these sites are closer to the ocean, and you have the southern mountain and you have the ocean, which kind of stabilizes the atmospheric turbulence. Why is this very important? Is that the stars, you see the twinkling, right? The twinkling is basically because of the atmospheric turbulence. So what this twinkling does is, when you're getting the rays from the star, it's because the stars are very far away from us, they are like a point source. But as it is passing through the Earth's atmosphere, the turbulence in the Earth's atmosphere will spread the light. Okay, so what is coming as a sharp beam becomes slightly fuzzy because of the turbulence. So this, we would like to avoid this fuzziness. The less amount of turbulence, the less fuzzy the image becomes, and this fuzziness is what we refer to as the seam. Okay? So we want to be at a site where the seeing is low, where the turbulence is low. And the Chilean sites offer some of the best locations which have very low seeing.
Okay, I want to ask. Okay, sorry. Go
Anupama,
ahead.
there is one more question in the YouTube. That is, Sovan Acharya is asking, I am participate as citizen scientist in participating probably in citizen scientist in Supernova Hunters project run by Zooniverse. So the question follows this: what is the maximum magnitude discovery supernova till now?
This is the maximum magnitude.
Magnitude, I think, probably
Probably faint end.
painter.
For the faintest end.
Yes, yes.
Faintest end, there are supernovae which have been discovered even at about 24 to 22nd magnitude.
Sorry, your last words were.
Yeah, we didn't get to that part.
Then I know for sure there are supernovae which have been detected close to 22nd magnitude
Okay.
Optical.
in optical, yes.
In optical. Yeah. I think earlier we mentioned that the historical supernovae which happened in our Milky Way probably have been very bright because they were naked as supernovae. So if
Yes.
you want to go to the other extreme, the brightest supernovae which were seen, probably you have to go to the historical records. Now the modern day supernovae which we see through telescopes are not as bright as those.
True. I mean, the brightest
Yeah, so that comes.
is
Go ahead.
Yes. Anupama, go ahead.
yeah, no, the brightest, and this is, of course, I'm looking at the apparent magnitude. Okay. So the brightest I think we have seen is obviously the LMC supernova because that was the closest. But I mean, this is just the apparent magnitude. This is not the actual luminosity of the supernova, right? More distant supernova can be really luminous, far more
Right.
luminous than.
The fact that we are seeing it itself tells you it is very
Tells you
luminous.
that it is a bright object. Yes, intrinsically bright object.
So you had mentioned that now with this automated surveys, nearly 2,000 or so are being discovered every day. I mean, was that the number you said?
No, about close to about 6,000 or so.
Oh, 6,000. So
In
this
a,
is all in different galaxies, right?
all in different galaxies. Yes, yes. In a
Oh,
year.
every day.
In a year. In a
In a
year.
year. A year. Okay. But in the Milky Way, we have not had for a long time.
At least the part of Milky Way which is visible to us.
Yes.
Haven't seen it.
Yeah.
Thankfully, we have not seen it. It will be so bright that.
So
Yeah, but
that
this.
actually brings me to the next question which I was itching to ask. If a supernova happens in our vicinity, what happens to the life on Earth?
It depends on how close it is happening. Right? I mean, it need not necessarily affect us, depending on where it is happening. It need not necessarily affect us. And you would probably see two, bright objects, two suns for a brief period of time, but not necessary that it's going to affect us.
So if suppose Betelgeuse, which is about 200 parsec away,
Hmm.
it actually becomes a supernova.
Hmm.
Who should we be worried about that?
Probably not. I don't think we should be very worried.
So we will get nice spectacular show in the sky, but other than that we
Yeah,
should not.
yeah, probably not.
And we can probably look for a black hole or neutron star once that happens, because in Milky Way it may be possible, right? In
Definitely,
other galaxies.
it's definitely possible.
So people also look at supernova remnants, right? Do they look for neutron stars and black holes by locating supernova remnants and trying to check if there's something there? Because of course they are very difficult to detect unless it's pulsating and not pulsating. Unless it is a pulsar, you will not be able to see the neutron star. But the progenitor, I mean, you may not be able to locate it, right? Unless it's a binary or some way. I'm just asking.
I remember having seen a paper where they have been able to detect the neutron star in a supernova remnant. I forget in which um, region of the electromagnetic spectrum they detected it, but I, yes, they did detect. But as you said, I mean, if there's a pulsar, it is the best way of detecting the neutron star.
So I'll come again. I'll come back again to slightly this supernovae which were seen by wider audience, not just astronomers. So 1987 you mentioned that you have seen in your lifetime. So what was your personal experience? How did you observe it? Where were you, and then what impression it had on you?
Oh, I had joined I already as a student by that time, and it was actually very exciting to be able to observe it, to actually get the spectrum of this object night after night. You know, we followed it up like an observatory program. So every night we were getting the spectrum. In fact, our observatory, the Vainugapur Observatory in Kavalur, was probably the only observatory in the northern hemisphere that observed this supernova. So we always say that in the 50 odd years of the existence of the Vainugapur Observatory, it has observed an object at minus 68 and another object at plus 63, a supernova at plus 63. Okay. So it was extremely exciting to observe this, and no, I always made it a point to go and stand on the catwalk and look at it naked eye. I wanted to see it, naked eye supernova. You can't miss out that, right? So when I'm observing, the first thing I do is I go out and I see this. Then we start the exposures. It was very exciting.
So, historically, there have been few supernovae, like crab supernova is one example where many cultures have actually recorded it. I think there are also papers about 1006 supernova being recorded by several cultures. And in medieval Europe, Tycho Brahe obviously observed a supernova, and Kepler observed a supernova. But we have not seen any such reference from India, very direct reference from India so far. So, what can be a reason for it? Why we missed all the supernovae which are very, very bright?
I, I mean, it's kind of difficult to say. It's quite, you might have seen it, but not recorded.
Yeah, because it is too bright to ignore. So, obviously, people would
Yeah,
have seen it.
nothing too bright to ignore, but um, I feel that much of the historical things in India were oral transmission, right? I mean, the actual recording it in form of writing or something was probably not in the same sense as in other places. So even if people have seen it, it might not have been recorded. But there are people who are actually trying to look at historical records and try to see if it had been recorded, but not directly as you find it in the other historical records, but in some other form. Like maybe in the form of some poetry or some painting or something, it might be there. One doesn't know, but I'm pretty sure that people would have seen it and noticed it and try to figure out what it is, but probably it's lost in somewhere in the
So,
oral history. Maybe it is lost.
coming back to modern astrophysics, you said that we are all made of stellar dust. And so most of these higher elements get formed in supernovae. So does it mean that the solar system is uh, is at a place where there was some supernova in the past, and then from that dust the solar system formed? So So if that is true, then should we expect some neutron star black hole in our vicinity?
It definitely see when in the early traces there would have been a lot more massive stars, and these would have evolved faster and enriched the chemical elements in the galaxy. The chemical enrichment would have happened. So the next generation of stars and planets which formed around the stars would be far more chemically enriched. But neutron stars could be there in the vicinity, and no reason why it should not be there. But
But we cannot pinpoint any existing degenerate object saying that this must have been the,
no.
because probably it has been too.
The other thing is that the Milky Way, the rotation is happening, so we may not be located today where we actually formed, right? So that is also another aspect that one needs to keep in mind.
So Samir wants to ask a question. Samir?
Yes, thank you, Anupama, for the talk, and it's amazing always to know about what Carl Sagan said, that we are all stardust, and supernova are kind of the place where all this stardust starts. In fact, just to point out, so this facility for antiproton and ion research in Germany is actually trying to recreate all the elements which happen in a supernova. So the question about CERN was, it's FAIR which is doing it rather than CERN. Yeah. I have a question which pertains to amateur astronomers. So we have a lot of them, very enthusiastic people, and many of them have a habit of looking at the sky every day and looking at the same portion of the sky and trying to hunt for supernovae. Now, with this, in this age of automation, with 6,000 supernovae per year, do you think it is still worthy to follow your hobby and try to look for supernovae in galaxies with a small telescope?
Yes, definitely. See, automated surveys, again, I said it's the cadence, right? So each of them have their own cadence, and not all of them could be coming back to the same region of the sky. Okay, and you don't know when a supernova happens. Now, these are located in the western part of the world. So when it is night for us and the supernova happens at that point of time, they're not going to be able to see it. So no reason why, even though there are these automated surveys happening, no reason why somebody can't follow their passion of looking for supernova. People still do it, and they do find supernova.
Great to know that.
So Anupama, there's this other thing, the growth project of which you are the PI. Is that also looking for supernovae? Is that one of the aims of that? Because it's
No,
going
we
to look
don't
for
search
transient.
for them. Yeah,
Okay.
we don't search for them. We do follow-up observations.
Okay.
So what is this growth project? Can you tell about it to our audience?
Yeah, so this is an international collaboration. GROWTH is an acronym for Global Relay of Observatories Watching Transients Happen. So it's an international collaboration having people from almost 12 countries who have access to telescopes, mainly optical infrared, but also radio and people who are part of the SWIFT collaboration and so telescopes in space. So essentially, it's like you try to have a 24-hour monitoring of these objects. Okay. So the philosophy is that when it is daytime in one part of the world, it is night in another part of the world. So you can have telescopes observing a particular object, and when slowly it begins to get daytime in that observatory, something else takes over. And the collaborators are spaced such that there is always some overlap between one observatory and another in time. So you can follow up some of the very interesting sources without gaps in the observations, weather permitting, you can do that. So the main sources of interest are young supernovae, the electromagnetic counterparts of gravitational wave sources, search for them, and near-Earth objects.
How long does this explosion typically last? I mean, I'm sure type 1a and type 2. So how long do astronomers observe that after the event has happened, typically?
So how long we can observe is basically depends upon how faint your telescope can take you to. But by and large, if you want to do a detailed follow-up, like for instance, we tend to start following up those objects that we can observe for a few months, especially the type 1 is about 2 to 3 months we can, and sometimes we have even observed objects for almost up to a year or more. It depends upon the brightness, basically, how faint it becomes.
From the energy, is it possible to tell whether it will become, the progenitor will become a neutron star or a black hole? I mean, in the sense, based on the brightness, can one do some calculations and estimate that?
That's right, because
if it's core collapse, of course, yeah.
In core collapse, you can actually, based on the observational properties, and combining it with modeling some amount of stellar evolutionary models and the explosion models, a combination of observations and theory does tell you what should be the mass of the progenitor and what could have been the core mass when the explosion happened. And based on the core mass, you say that is either a neutron star or a black.
Okay, thank you. So, Aniket, Harvinder, are there any more questions? Or shall we wind up for today?
I
Yes.
have one
No.
small
Yeah,
question.
Yes.
Go ahead.
Yeah.
So in between, we saw some papers that type 2C supernova, which is associated with gamma ray bursts, can be standardized. Is there anything more than that? Because I haven't seen much more on that path.
The type 2 piece you're talking about?
Yeah, type 2C, I think, with associated with gamma ray bursts.
See, people are looking at whether the gamma ray burst can be used as standard candles. People are working on that, but we don't have enough numbers for it to be a statistically meaningful result. But there is a type of core collapse supernovae called the type 2Ps, and these are supernovae which have a constant luminosity phase during its decline. And by actually studying these objects during the constant luminosity phase, one can get an indication of the distance to the object. So the type 2P supernovae are also looked at for distance measurement as candles. Candles.
Yeah, thanks.
Aniket, you have some more questions? I mean, some.
No, I think we will wind up for today.
Okay.
Harvinder, anything from your side?
Yeah, can you just sum up the discussion and wind up?
Yeah, so it was very nice to start off our discussion sessions, and it was very concisely put, and lots of things were covered, which I'm very, starting from how stars were born, how have stars evolved, and how they end their life and what remains afterwards. And it was very exciting to see, understand also what is the importance of supernova, and how in different fields they are very important, and in cosmology, and how they can be standardized as how supernova type 1 are standardizable candles. So it's very exciting, and I hope that people who watch it later, who are watching it and are watching later, would be excited to know about this field more. And and I would like to now thank the speaker for giving such a fantastic talk. And also, I would like to thank IIST and ISER Mohali administrations who have given the infrastructure to hold these talks, and Samir who has agreed to help with the logistics of streaming it on, and various other technical difficulties that we earlier had faced, and he sorted them out. Thanks a lot. And we will meet in the session Ask an Astronomer on second Sunday of December, which is 13th December. And we'll let you know what the topic is. So see you there at that time on the audience that you have. And do tell your friends to join in into this. Thanks a lot, Anupama. Thanks
It was nice.
a lot.